In the last segment, we saw that Ka and Kb interact through Kw. And this idea that acids and bases can react with each other is going to turn out to be really, really powerful. So let's start by asking the question, what happens when we mix weak acids and weak bases? For this example, we're going to pick a classic mix that are a set of concentrations and compounds that at this point you might be rolling your eyes with a little bit, but one that's going to be pretty useful in showing an example of how these behave. So let's imagine mixing together 0.025 molar acetic acid and 0.025 molar sodium acetate. So we're adding together a acid and its conjugate base. From the previous calculations that we did of an acid and a base, you would probably expect that this should be pretty acidic, and this won't be really all that basic. Okay, well, what else? How do we approach this? If you recall, when we were solving equilibrium problems, one of the things I said was that you should never start to tackle one of these problems without the chemical reaction equation. In understanding the behavior of this combination, what we really need to pick up is our reaction. We just said we're adding these together, so they must be the two reactants, right? Not quite. We want to determine the pH of this solution. We need one more piece of information, by the way. We need the pKa, which is equal to 4.77. So if we're going to figure out the pH, that means we care about H+ concentration. So that means the best equation to use to describe this reaction is our acid reacting to form H+ and our conjugate base. In essence, what we've done here is add together some reactant and some product, and the question is, how much of each are we going to get? So one of the first misconceptions that you want to conquer in understanding buffer problems is appreciating that even though we're adding these two together, that doesn't mean they're both reactants. If you think way back to when we talked about Gibbs free energy, remember that delta G is ultimately the thing determining which way a reaction wants to go. Now, with that said, how do we figure out what our pH might be? Well, we need all the same tools that we were using to determine pH when we had just a weak acid. So that means we want a Ka expression. Same old Ka expression, nothing new here. And we're going to want to make an ice table. Again, nothing's really new so far. When we go to start filling this in, however, things are going to get potentially a little bit interesting. So our initial amount of acetic acid, our initial amount of acetate, and our initial amount of our H+. Now, you could also probably get away, at least much of the time, with putting 0 here, but remember this is the equilibrium amount of H+ that would be floating around in neutral water if you dumped both of these in. Since we're adding in an acid and a base, it's not really clear which way this thing is going to go, so it'd probably make sense to have some H+ in here to make sure. So, what's our change going to be? Well, this probably looks quite a bit like the sorts of problems that we ran into when we were looking at determining the pH of some solution of acetic acid on its own. In essence, we have a pKa, so we have this part, but we don't know how much H+ is going to be formed. So we're back to one of those cases where our ice table is going to have an unknown. So we're going to be relying on our stoichiometry. In essence, we know, based on this chemical reaction equation, that any amount of acetic acid that is consumed must produce an equivalent amount of acetate and H+. Okay, so we're moving forward in much the same way we did solving a weak acid problem. And that is, perhaps, starting to look a little bit scary. Again, this may be asking us to do some pretty hefty algebra. Nothing too crazy, but we may be having to bust out the quadratic formula. However, recall that when we were dealing with a weak acid, we said we could probably neglect the amount being lost. If we can probably neglect the amount being lost, that must also mean that we can probably neglect the amount being gained. We're going to check in just a moment to see if that's actually the case. If it is, however, that would mean that this both of these concentrations would be effectively unchanged. That would sort of paradoxically mean that this buffer problem, where we added in more stuff, could actually be easier to solve. So, now that we have that, are we ready to plug everything in to that Ka expression? Well, not quite, right? We were given a pKa, and we need a Ka. If we convert, we'll find that that Ka is equal to 10 to the negative 4.77. That equals 1.7 times 10 to the negative 5. So, now we're ready. Concentration of our base times X well, that's interesting. That cancels right out. That says X, which is our concentration of H+, should be equal to 1.7 times 10 to the negative 5. Now, here's a place where you might be looking back at that X. Should that X really be 1 times 10 to the negative 7 plus X? We put this in, could we really neglect it? Well, taking a look here, that makes this 7 10 to the negative 6 place, so that 1 would be all the way back here. As was the case previously, this x and this 1 times 10 to the negative 7 is truly and literally insignificant. That is, from a mathematical standpoint, it does not make a significant difference. So that means that all of these are insignificant. That may not always be the case. What I want you to do is effectively what we just did. When you get your number and you go, okay, I just figured out what x is, I want you to come back up here, plug x into these values, and make sure that it really is insignificant. If not, you can't get away with those kind of neglecting the insignificant parts anymore, because those parts are no longer insignificant. What else does this mean? Well, we got this number, which you'll recall is now our H+ concentration. We got that number from our pKa. So we can plug that right back in, and now our pH is going to equal 4.77. Hold on here. Isn't that our pKa? Well, when you have a buffer in solution, at least significant enough amounts of it, by which I mean if you made your amounts really, really, really tiny, the equilibrium of water itself could get in the way. But for most common amounts, if you put an acid and its conjugate base into solution, you make a buffer, and that buffer, if present in equal concentrations, will have a pH equal to the pKa. Up next, we're going to be expanding from here to look at what buffers are good for. Now, you may have added something like tris buffer or phosphate buffer to an experiment in a course like biology in the past. What we're going to see in our next segment is that buffers like this are so interesting because they resist changes in pH. So that's coming up next.